So today we'll kind of review a few of these concepts that were asked about on the quiz. But before we jump into that, I wanted to revisit our square root of not gate that we were talking about at the end of last class. And I figure there's one semi-important concept to clear up. I had some interesting conversations with people after class, and I realized that there was something missing. So, all right, here's our square root of not gate. We showed that it was unitary, so the matrix times its conjugate is equal to identity, or its inverse is equal to the adjoint. That's all good. But the thing I asked about second, I think, was about the determinant. And so we know that the determinant of a unitary matrix, the magnitude of the determinant of a unitary matrix is equal to 1. And so for a complex unitary matrix, this means that it will be on the edge of the complex unit circle. So if I draw my unit circle, I have 1 and minus 1 and I and minus I, things in between. So anything, so the determinant doesn't have to be 1. It could also be I, it could also be minus I, it could also be anything else that's on that unit circle. So when we do this determinant, we're going to get that it's equal to 1/4 times 1 plus I, 1 plus I, minus 1 minus I, 1 minus I. And that's going to end up being 1 plus 2I plus I squared minus 1 minus 2I plus I squared. So 1/4 times 4I. So that's I. That's okay. It's okay that it's not 1. It's still on the unit circle. So it still conforms to our requirement for determinants for unitary matrix. Yeah, you can also think about this if you write down the very general form of a unitary matrix. It looks something like this: A, B, minus e to the I phi B conjugate, e to the I phi A conjugate. And the determinant of this matrix is e to the I phi. Cool. Okay, good. All right, so your sort of reading this week and what we talked about in class was all about what can we learn about qubits from thinking about the properties of a single qubit. And so some of the things that we can learn are distinctions between classical mixtures and quantum superpositions. We learned about the concept of the density matrix. We talked more specifically about the normalization constraint and probability amplitudes. We talked a lot about the global phase and kind of mapping from the complex plane to the Bloch sphere. And then we talked about gates of all sorts and shapes. But we also especially mentioned the Hadamard gate and its utility in initializing superposition. So let's review a few of these. So when you think about the idea of the distinction between classical mixtures and quantum superpositions, what comes to mind? It's discrete, right? Like a good property of a classical mixture is discreteness, binary, water and oil. Okay, that's a good example. Another property of a classical mixture is that you require sort of multiple measurements to get a distribution. It's governed by statistical mechanics. So what about superpositions? How are they distinct? So it can't be represented as a mixture. It's sort of continuous, not discrete, not A or B. It's A and B. So there's more than two options in a superposition, right? Like you have 0, you have 1, and then you have alpha times 0 plus beta times 1. In our qubit, we have a ground state and we have an excited state. It's two discrete states. But the interesting thing that quantum mechanics tells us is that we can have those two states, and then we can have every other possible combination of those states based on probabilities. So enter the density matrix, right? So what is the density matrix? If we wanted to think about an analogy with a classical mixture, what would the analogy of the density matrix be for a classical mixture? So it sort of plays the quantum role of a probability density. And why do we need it? We need it in our discussion of qubits to be able to deal with mixed states. And for things not to get too crazy. So we introduce it so that we can handle mixed states in just the same way that we handle pure states. So it allows you to pull a probability matrix out of a quantum state. It encodes all the accessible information about quantum systems. And it looks like an outer product of the state with itself. If we think about the Bloch sphere and mixed states, pure states, so we have our sphere, my two-dimensional projection of a sphere. If we're on the surface of a Bloch sphere, that's a pure state. If we're anywhere inside the Bloch sphere, that's a mixed state. And the center of our Bloch sphere is our maximally mixed state. So a fun example of thinking about pure versus mixed states comes from thinking about the polarization of a photon, or of light in general, sorry, polarization of light. So an individual photon can be described as having right or left circular polarization. So we can write it as R or L. And we can also describe it by a superposition of the two. So we can describe it as alpha R plus beta L. And we know alpha squared plus beta squared equals 1. And the sort of limits here and what alpha and beta are can kind of give us linear polarized light or circularly polarized light or elliptically polarized light. So what state of our photon would give us linear polarized light? So that would just be if we had alpha or beta equals 0. And what would give us circular polarized light? Alpha equals beta. And what would give us elliptical polarized light? Anything else? You got it. Okay, so if we are going to, let's consider vertically polarized light. We'll call it V equals R plus L divided by square root of 2. So this is a polarization state for our light. We have the coefficients on R and L the same. If we pass this vertically polarized light through a circular polarizer that only allows R polarized light or L polarized light through, then half of the photons would be absorbed in both cases. So if we pass it through circular filter, half of our photons get absorbed. That makes it seem like half of our photons are in the R and half of them are in the L state, but that's not right. So if we pass that same vertically polarized light through a linear polarizer, there wouldn't be any absorption. Okay, so what happens when we talk about unpolarized light? Unpolarized light is like what you get out of an incandescent bulb. And the polarization state of our photons is completely random. So unlike polarized light, it passes through a polarizer with 50% intensity loss, whatever the orientation of the polarizer. So I can write down the density matrix of this unpolarized light because I can describe unpolarized light as a statistical ensemble. It's not a superposition state, but it can be described as a statistical ensemble. So I could write down rho equals 1/2 R outer product plus 1/2 L. And that's the same if I wanted to call them horizontal and vertically polarized light. That would be fine. They would be the same. You couldn't distinguish between them. And I could write down, this is going to be 1/2 times the identity matrix. So it's just 0.5, 0, 0, 0.5. So this is kind of a fun example. It gives you a really clear intuition for the situation when you have pure versus mixed states. There's other ways to generate unpolarized light. So one possibility would be to generate or introduce some kind of uncertainty in the preparation of our photon. So if we passed it through a birefringent crystal that had a rough surface so that slightly different parts of the light beam acquired slightly different polarizations, that would be a way to make a mixed state. Another possibility would be to use entangled states. So, for example, radioactive decay can emit 2 photons traveling in opposite directions. And the quantum state for that would be written down as something like R, L plus L, R over square root of 2, for example. The joint state of the 2 photons together is pure, but the density matrix for each photon individually, which is found by taking the partial trace of the joint density matrix, is completely mixed. So that's kind of a fun. Light's cool, and we'll talk more about light as a quantum thing next week when we kind of talk more about the physical properties needed to be a qubit and the concepts of coherence and all of that. Okay. What about normalization constraint and probability amplitudes? So one thing that I think is useful to think about when you're sort of formulating an understanding of these superposition states is to remind yourself sort of what all of this needs to look like and how all of the different representations of our quantum state are related. So if we write down our generic quantum state alpha, superposed quantum state alpha 0 plus beta 1, we remember that these zeros and ones, they represent vectors, 1, 0 and 0, 1. And the sum of the probabilities need to be 1. And this idea, came from Max Born, and he told us that alpha squared plus beta squared equals 1. That's our normalization constraint. And so when we have complex alpha and beta, then we have, we can write a complex number like z equals x plus iy, and the absolute value of z squared, which is just z times its conjugate, needs to be x squared plus y squared. And that's a unit circle of radius 1 again, or complex unit circle. And so then we can introduce polar coordinates. We can change our coordinates. So we can call x equals r cosine theta, y equals r sine theta, z equals r cosine theta plus I sine theta. And then we can use Euler's identity to write down that z equals r e to the I theta. So that gets us another way to write down a quantum state. And we can write it down as r alpha, some real constant, times e to the I theta alpha times 0, plus r beta, e to the I theta beta times 1. And the problem with this form of the quantum state is that it has 4 unknowns. It's a little bit complicated to work with. So we have r alpha, r beta, theta alpha, theta beta. And so there's a way to kind of simplify our lives and describe this more in context of the Bloch sphere by taking advantage of the global phase. So if we have 2 quantum states differing only by a factor of e to the I theta, then they're indistinguishable. That's kind of what the global phase tells us. So I can write down some new quantum state, psi prime. It's e to the I, we'll call it minus I theta alpha times psi. So that lets me rewrite this by plugging in the equation I just wrote on the last slide. E to the I theta alpha times r alpha e to the I theta alpha 0 plus r beta e to the I theta beta 1 and then I can further simplify this. So now I just have r alpha times 0 plus r beta e to the I theta beta minus theta alpha times 1. And then you can just simplify your theta beta minus theta alpha, just call it theta. And this gets us down to just having 3 parameters, r alpha, r beta, and theta. So then you can introduce your spherical coordinates back into the ball game. So x equals r sine theta cosine phi, y equals r sine theta sine phi, and z equals r cosine theta, and then you can come back to the Bloch sphere. That gets us to psi equals cosine theta over 2 times 0 plus e to the I phi sine theta over 2 times 1. So I feel like as I was myself learning all of this. I was kind of always struggling to know which state I should be thinking in at any given time. And I think just walking through it once, kind of continuously to see how you go from one to the other is somewhat useful. All right. Let's talk about the Hadamard gate. So the Hadamard gate is the thing that we use to kind of put our qubit into a standard superposition. And it's equal to 1 over square root of 2, 1, 1, 1, minus 1. So we're doing a 90-degree rotation about y, and a 180-degree rotation about z. And what does it do to 0 and 1? It takes them to the equator. So it creates a superposition such that you have equal probabilities of getting 0 and 1 when you measure it. And one thing that we'll see next week is like this is how a lot of NMR experiments work. So you start with your ground state of your nuclear spin, and then you apply a 90-degree pulse, and then you let it relax, and then you bring it back up to measure it. That's, yeah, it's exactly the same stuff. Okay. Anything more to say about Hadamard gate? You guys are good with that? All right. So I had you guys read a little bit about Felix Bloch, his nuclear induction experiments, and a lot of the concepts when you think about NMR are going to come into play when we're talking about T1 and T2 times and coherence next week. But I think it's pretty interesting that his theory of nuclear induction, which is not super related to the Bloch sphere, were just so kind of intrinsically coupled. And when you try to track down, like, why is the Bloch sphere, like, why did they name it after Felix Bloch, it's kind of hard to, like, map out that history. So maybe just to start, what did Felix Bloch discover that he won the Nobel Prize for? This idea of nuclear induction. Anybody give this, maybe even just the really short paragraph paper a read, or the Nobel lecture a read? So what he found was that under the effect of an external field, the magnetization vector relaxes to its equilibrium configuration while processing around the magnetic field. And that's exactly what's shown in this picture. So under an external B field, the magnetization vector relaxes while processing around the magnetic field. And it processes about the field with a latitude that decreases as the frequency of the oscillating field approaches the Larmor frequency. So when the frequencies near this magnetic resonance frequency, you can expect an oscillating induced voltage in a pickup coil with an axis that's parallel to the y direction in this experiment. And so that's, I mean, that is NMR. So he took water and he observed the signal induced in a coil by the rotation of the proton moments in his water sample. And he even went further to kind of test this idea, and he added some paramagnetic manganese salt, I think, and he called it a catalyst to accelerate this relaxation to equilibrium, so that he could test this idea of where the the shift is, where that resonance is in his experiment, so he could perturb it by messing with the relaxation time. These pieces of work that he did were sort of started in sort of January. He published that first little paragraph paper in January 1946, and then I think he published the big follow-up paper, which I didn't assign you, but you can easily find, in July of that same year. So in the little paper, he was like, yeah, we did this stuff. It's really cool. Trust us. And then like later on, he told you more about the details. And that's what he won the Nobel Prize for. And so what these papers do that connect to the Bloch sphere, and maybe you can even tell from the diagram here, is that they sort of establish this concept of a rotating coordinate procedure. So when you look up things like this, it's like dr, dt, so you're looking at the change in r with time. It's equal to this some perturbation, omega times r. So the magnetic interaction with a spin 1/2 system is the thing that he was considering, and this r space reduces to real physical space. And what he did is observe how r varies under the action of different types of perturbations, omega here. And he used this idea of a sphere and like moving around on the outside of a unit sphere to describe this stuff. And so down the road, when like Feynman and all these guys, were starting to think more about quantum information, they attributed this idea to Bloch. And so it got called the Bloch sphere later on, and Bloch never even drew a sphere in any of his papers. So you'll see this idea of rotating coordinate procedures mentioned, and that is the connection between the Bloch sphere and what Bloch did with nuclear induction. So not super straightforward, but interesting nonetheless to kind of try to track down. So like I said, next class we're going to learn a lot more about what he found here in terms of these relaxation times. So there's two key relaxation times that govern this approach to equilibrium, and they're a T1 relaxation time and a T2 relaxation time. And these are the things, the properties that dictate whether your two-state system is of any practical utility as a qubit. I guess one thing I'll mention is that all this like rotating coordinate procedure stuff led to the Bloch equations, and they're what's used to calculate magnetization as a function of time when relaxation processes are present. So these T1 and T2 times. And they're often referred to as the equations of motion for nuclear magnetization.